Good morning. Today we're going to start our discussion of Chapter 11. This chapter is going to be the first in sort of a two-part discussion where in Chapters 11 and 12 where we're going to talk about the phases of matter. So we're going to talk about gases and the behavior of gases in Chapter 11. And then in Chapter 12 we're going to talk about liquids and solids and dive into more things like phase changes and how we can look at those kinds of behaviors. But before we get too far ahead, let's just look at gases. So we spend the most time looking at gases because there's a lot of information known about gases. They have some very nice properties that we can look at and get some really good information. So we spend a little more time developing our discussion about those and establishing some equations that relate certain key properties of the gases to each other. But let's start first of all with how we think about gases or how we understand the behavior of gases. So we use a theory called the kinetic molecular theory, which is really just a theory about how molecules of gas move, right? Kinetic movement, molecular molecules, so really a theory of molecular movement of gases. And so this model is predictive, right? It works really well under most conditions to predict the correct behavior of gases. But like all models, it's not perfect, right? There are things that it doesn't predict or conditions under which it breaks down. Now, in this course, we'll focus on conditions where the kinetic molecular theory works well. So let's look at the theory. There are four big points that we want to think about in this theory. First of all, we assume that gases are made up of a collection of particles or molecules that are in constant motion. We also presume that those molecules are not attracted or repelled from each other. So in essence, they act as independent entities moving around. And when they do collide with each other, we think of these collisions like we would the collisions of, say, two pool balls or billiard balls with each other, where they don't smush into each other. There isn't really any kind of loss of energy. They just simply bounce off one another. Now, they may pass energy from one to the other. So one may come in and transfer some energy to another, and so the other one leaves moving faster, and the one slows down. But they don't stick to each other, right? They just bounce off each other like we imagine billiard balls doing. So we have molecules in constant motion. They're colliding and bouncing off one another. We also make the assumption that there is a lot of empty space between the particles, right, compared to how big the particles are. So really what that means is in any sample of gas, the vast majority of that sample is empty space that the molecules are moving around in it. But the space occupied by the actual molecules themselves at any given time is small. And the last thing is the speed of the particles increases with increasing temperature. So as we raise the temperature, we raise the velocity or the speed that the molecules. Remember, temperature is simply a measure of the average kinetic energy of the molecules of a sample. So if we have a higher temperature, it means the particles have a higher kinetic energy or they're moving faster. So taking into account these four tenets, we're going to look at some behaviors that we can explain these, or look at how these ideas help us explain some different ideas. So, with that intent, we can say that the kinetic molecular model is consistent with the properties of gases that we know, right? And so we'll look at a few of these properties. So first of all, the average kinetic energy, right? The temperature, right, is energy due to motion. So the gas particles are moving, and as the temperature changes, those gas molecules move faster. Now, specifically, it's proportional to the absolute temperature, or what we call the Kelvin temperature, right? So a lot of times in gases, when we do these gases, we'll see the Kelvin scale, because that's where we see this proportionality the simplest, right? So this means that as the temperature increases, the particles move faster and therefore have more energy. Now, we also will look at the idea that gases are compressible and how the kinetic molecular theory can help us understand that. And gases have very low densities in comparison to liquids and solids. And then finally, gases adopt the shape and volume of their container, right? We know that. So this first idea about compressibility. So gases are compressible. They're the only phase of matter that is compressible. And simply what that means is that we can change the volume, right? And this comes back to the idea that we talk about, that under the kinetic molecular model, there is a lot of empty space between the gas particles. So if we look at our picture, right, if here we start out with a lot of empty space, we compress the volume, what we're simply doing is taking up some of that empty space. So we're making less empty space. So we can lower and raise, and we simply push the gas particles a little bit closer together to change the volume. So we're compressing it in from a large volume into a small volume. We can't do that with liquids and or solids, right? Liquids are already as close as they will get to each other, so we can't push them any closer. So liquids and solids are non-compressible. Gases, we stated, had very low density in comparison to their solid and liquid counterparts. And so again, because this idea that there's so much empty space between the atoms or molecules, right, there's going to be a lot of volume for a given mass. So remember, density, right, is the ratio between mass and volume. So if we have a very low density, that means a given mass is in a large volume, right? So if a given mass is in a large volume, we have a very low density. And that's what we have with gases, right? Because we have a large volume because of all that empty space. So to give an example, if we had liquid water occupying a volume of 350 milliliters, and we evaporated all of that liquid into a gas, so instead of steam, right, and we let that expand, right, the steam would occupy a volume of 595 liters, right, under the same conditions. And so that would be equivalent to about 1,700 soda cans. So the idea is that when it exists as a gas, right, the same amount will have a much larger volume and therefore a much lower density. So the density of steam at 1 atmosphere and 100 degrees temperature is about 0.0006 grams per milliliter. Now remember, the density of liquid water is about 1 gram per milliliter. So much, much less dense. Now, lastly, we know that a gas assumes the shape of its container, right? And this again goes back to one of the tenets of our kinetic molecular theory, and that is that there are no attractive forces between the gas molecules. So they have the freedom to spread out to in as much space as they can, so they will assume or adopt the shape and or volume of their container, since the molecules are not attracted to one another. And this gives rise to the fact that we have a lot of empty space, right? This is the reason why we have so much empty space. Right? So we have these particles in constant motion, without attraction, so they will expand to fill their container, creating a system where there is a large amount of empty space in between the particles. So one of the key properties of gases is this idea of pressure. So the pressure of a gas is the result of constant collisions of the gas particles between the atoms or molecules in a gas and the surfaces around them. So if we think about this gas, right, as a collection of particles in constant motion, right, they're going to move until they hit something, right? So that something might be the walls or of the containers that are holding them, right? And that's going to create pressure. Now, if we have, say, gases in a high density, right? So when we compress them, right, we're going to create more pressure. If we have a lower density, right, bigger space between the molecules, they're not going to hit the walls so often. It's going to create less pressure. So as we go through this and we try to think about pressure, one of the key things that we can think about them is that more collisions equals more pressure, right? There is a connection there. You know, if we do something to change the number of collisions, we're going to result in changing the pressure. Now, there's lots of sort of normal everyday phenomenon that can be explained by thinking about pressure, such as drinking from straws, inflating balls or inner tubes, right? And in fact, simply breathing, right, can be explained based on these ideas of pressure. Now, one of the most important areas where we think about pressure is in the way that we live, right? We live in a sea of gas, right? So just as fish swim around in a sea of water, right, we swim around or move around in a sea of gases, right? So we're being constantly bombarded with gas particles. Now, we don't feel them because we've adapted to this environment, but we are being constantly bombarded with molecules of what we call air, right? Nitrogen, oxygen, water vapor, carbon dioxide, other gases that make up the air around us. Now, of course, because this is a gas, it has a pressure, right? And we think of this, or we call this, the atmospheric pressure, right? And so the atmospheric pressure is responsible for a lot of phenomenon, such as wind, weather, and the pressure in and around us, right? And so we'll bring this up at different points along the way. Now, the pressure exerted by a gas sample can be defined as the force per unit area. So if we think about the particles colliding with a surface, they are hitting that surface and imparting a force over a certain amount of area. And so the pressure results from all these collisions with the surrounding surfaces. And the amount of pressure depends on a few facts, right, or a few variables. Right? So these include how many gas particles we have, right? The more particles, the more pressure in a given volume, and other things like temperature that we'll get to as we move along. So another sort of interesting idea that we're all familiar with, that we think can associate with pressure, is the fact that atmospheric pressure, right, the pressure of the air around us, changes as we change altitude, right? As we move further away from the surface of the Earth, the pressure gets lower and lower. Now, we just said that the pressure is related to the number of particles, and that's exactly what's going on here. As we move to higher and higher altitude, the the sheer number of gas particles decreases, right? And so we say that the atmosphere or the air gets thinner as we move to higher altitudes. And what that really means is there is just less gas particles, more empty space, lower pressure. And so as we rise up, like in an airplane or drive up a mountain, right, we notice a pressure decrease. And we often feel this in a physiological way where we experience pressure in our ear canals, right, as the altitude changes. And so the idea is that the pressure is getting lower outside as we rise up in altitude, but the pressure inside are the cavities in our head, right, which is where we maintain our internal pressure, right? This maintains our equilibrium and allows us to balance, right? Most of that is done through maintaining an equalized pressure using the ear canals, right? So we want the pressure inside the empty spaces in our head, the cavities, right, the sinus cavities, to be the same as the external pressure. But if we see sort of sudden changes in this external pressure, our internal pressure can't adjust fast enough, and we experience a sensation or maybe a pain or a popping of our eardrums. Now, not an actual popping meaning a damage, but it vibrates kind of like the top of a drum. Right? So as the pressure adjusts, the eardrum allows that airflow in and out to equalize the pressure. And when it does this fast enough, right, it creates a bulging and a popping sound. Now, if there's something preventing this from happening, like congestion in the cavities, this can cause some pain and we can get pressure in the ears or a momentary pain until we can get that pressure to equalize, until we can get the air to escape, getting that pressure back to normal. Otherwise, we feel that bulging of the eardrum as a pressure or sometimes a pain. So the simplest units of pressure. So anytime we have a unit or a property here that we're going to look at, we have to have a scale, a units to express it in. So there's several units of pressure that we'll talk about. The most common one that we see is what's called the atmosphere. This is the most common one in chemistry, and this is the ATM, or the atmosphere of pressure, right? And this is just simply the average pressure at sea level, right? So this was assigned the value of 1 ATM, or 1 atmosphere of pressure. Now, the SI unit is what's called the Pascal, not something that we use too terribly often in chemistry, more so in physics. And a Pascal is a much smaller unit of pressure than an atmosphere, and we see that 1 atmosphere of pressure is equal to about 101,000 pascals. Now, you don't need to memorize this conversion factor, but you may be called on to convert between the two units. Now, a third unit of pressure is something known as a millimeter of mercury. So this is a very old unit of pressure, one of the sort of original units of pressure, and it comes from how pressure used to be measured using a barometer. So if we look at this drawing over here, right, this is a mock-up of something what an original type of barometer would have looked like, where we have a pool of mercury, and within that, or put into that, would be a glass tube that had been evacuated, right? So remember, if we put something under a vacuum, it means that we remove the gas, or, reduce the pressure. So the idea is that in here we have very low pressure. So it's under a vacuum. So we have an area of low pressure inside this glass tube. We have atmospheric pressure pushing on the pool of mercury. And as this, we have a pressure difference this pressure pushes the mercury up the column, and that column will rise until the pressure of this mercury downward, just due to gravity, right? So the pressure of this column downward equals the atmospheric pressure that's pushing upward. When those two are equal, then this column will stop rising, and whatever the value is here, that is a measure of atmospheric pressure, or the pressure of the air. And that was measured in millimeters of mercury. And so it turns out that the average atmospheric pressure in millimeters of mercury at sea level is 760 millimeters of mercury, or 29.92 inches of mercury. Now, we just said that 1 atmosphere of pressure was defined as the pressure at sea level. So what that also leads to is that 760 millimeters of mercury equals 1 atm of pressure. Now, some of you may be asking why we used mercury here. Now, nowadays we don't use this kind of barometer, right? We can have closed mercury barometers, or we can use other types of devices to measure the pressure because of the toxicity of mercury. But the reason mercury was used is because it was a liquid, of course, and it's a very, very dense liquid, right? It's 13 and a half times more dense than water, so that we won't have to get the same amount of mass, right, in this column, we don't need it nearly as high a column, right? So this volume is going to have a lot of mass because of the high density. With water being lower density, right, it's going to take a lot more volume to get the same mass. And so, in fact, we would need a column about 13 and a half times taller, right? Or almost 10 meters high, or a little over 10 meters high, and that's about 30 feet, right? So we would need a column about 30 feet high if we wanted to measure atmospheric pressure with water. So this is why we don't do that. So just to reiterate some of the units of pressure here. So the big, most important conversion factor is this idea that 1 atmosphere of pressure is equal to 760 millimeters of mercury. And this is a conversion that you want to become familiar with, right? You're going to use this one quite often. Now, another thing that you might see is that there was another name given to a millimeter of mercury, right? It was named after an Italian physicist named Torricelli, who invented the barometer. So if you see the unit of a torr, that is exactly the same as a millimeter of mercury. So 1 millimeter of mercury is also equal to 1 torr. So you may see either of those two units being used. One of the more common everyday units of pressure is something called the pounds per square inch, or PSI. This is the common unit that's used when we inflate things like tires or basketballs or other things. We inflate them to a certain number of PSI. And 1 atmosphere of pressure is equal to 14.7 PSI. So typically, if we want something to be inflated and rigid, right, and we would inflate it to greater than 14.7 PSI of pressure, because we need the internal pressure to be higher than the external pressure so that it doesn't collapse. So I mentioned at the beginning that one of the common phenomenon that we see, that we use to explain with pressure, is drinking out of a straw. So let's look at our barometer, right? Our barometer works much like a straw. So if we sit over here and we draw our cup, and our cup has some liquid in it. And let's say we have a lid on this cup. We have a straw. Oops, that's a very wavy straw, but we'll get the point. Now, outside this straw, right, pushing down on the liquid, just like we have a barometer, right, is atmospheric pressure. Now, when the cup is just sitting here like this, right, atmospheric pressure is pushing down here too. But if we go to drink, right, and I'm going to draw this just as we have somebody going to drink out of this straw here. When we drink, we pull the gas out, and it creates low pressure inside the straw, just like we have in our barometer over here, right? So we have low pressure inside the straw because our drinking, our, if we want to say sucking on the straw, right? What we're really doing is sucking some of the air out of the straw, creating an area of low pressure. Now, when that happens, then atmospheric pressure can push down, and as it pushes down, we actually push, atmospheric pressure actually pushes the liquid up the straw into our mouth, right? In fact, we cannot exert enough pressure to pull the liquid up. We can only remove the gases, and atmospheric pressure does the rest. And just like it does with the barometer, it pushes the liquid up the straw, and so we drink. So drinking out of a straw works much like we see with the classic barometer. So I just want to close this area of looking at units of pressure with an example of a pressure conversion, right? So one of the most common ones that we're going to be doing here is converting between atmospheres and millimeters of mercury. And remember, just like any units conversion, we have a conversion factor. So in this case, right, it was 760 millimeters of mercury equals 1 atm. So we can set that up as a conversion factor in whatever's on top, depending on what we start with and what we're trying to find. So in this case, if we start with atmospheres, we're going to want our 1 atm on the bottom and our 760 millimeters on the top, so that our atmospheres cancel out. We end up with millimeters of mercury as our final unit, and so we do our math, and we get that 0.311 atmosphere equals 236 millimeters of mercury. So as we go and continue to talk about gases, this next section we're going to talk about a couple of fundamental properties of gas, a couple of laws of gases that relate some of the properties. So as we look at this, we're going to think about 4 fundamental properties of a gas. We're going to have pressure, we're going to have volume, we're going to have temperature, and later on we'll talk about moles of gas. But for now, we're going to look at 2 laws that relate pressure, volume, and temperature to each other. So the first one of those is what we know as Boyle's law. And what Boyle's law says is that the pressure of a gas sample depends on its volume, right? And so if the temperature and the amount of gas are constant, right? So if temperature and moles of gas are constant, then an increase, the pressure of a gas will increase for a decrease in the volume, or a decrease for an increase in the volume. So we say this is an inverse relationship. So the volume of a gas and its pressure are inversely related, right? So in other words, as the pressure goes up, the volume goes down. As the pressure goes down, the volume would go up, right? They move in opposite directions. And so, and we can relate that proportionality like this. So the volume is inversely related to pressure. So one of the common examples that we see this in is a bike pump, right? So if we have our bike pump, right, we have essentially a piston inside that bike pump. And as we pull the piston up, we increase the volume inside the piston here. So we increase the volume here, which will lower the pressure, right, inside here. Now, on the downstroke, where we are compressing the gas, right, we're decreasing the volume, which is going to increase the pressure, right? So this goes back to the compressibility of gases, right? As we compress that gas, we move the gas molecules much closer together. They're going to have more collisions. They're going to increase the pressure. So volume inversely related to the pressure. Now, the same concept of Boyle's law is how we can explain the basics of breathing as well, right? We breathe because of Boyle's law, or we can think about it in terms of Boyle's law. So if we think about breathing, right, if we inhale, right, so if we pull air into if we start the inhalation process, right, our lungs expand, right? So our lungs expand, we create more volume, right? And as there is more volume, right, the pressure will decrease. Right? As the pressure decreases in our lungs, we get a pressure difference like we talked about with the ears. So by increasing the volume in our lungs, we decrease the pressure. Now the pressure in our lungs is lower than the pressure outside, and so air flows in, just like it would flow out of our ear, right, if the pressure was less. So we're always going to get airflow. I want to think about this. Airflow from high pressure to lower pressure. And so when we increase the volume of our lungs, which lowers the pressure in our lungs, air flows in because we have high pressure outside, low pressure inside. And during the exhalation process, right, our lungs collapse or get smaller. We decrease the volume, which increases the pressure. Now the pressure inside of our lungs is higher than the external pressure, and so air flows out, right? It flows from that high to a low, and we get the exhalation. So this inhalation, or this inflation of our lungs, followed by draws air in. The deflation of our lungs then causes air to go out, and we get breathing. Simple as that. Now, if we go back to kinetic molecular theory, we can remind ourselves of how kinetic molecular theory can explain what's going on here. So if the volume of a gas is decreased, like we just did, if we look at it from a molecular level, right, we have the same number of molecules here. So the same number of molecules here is here, but now they occupy a smaller volume. They are closer to one another. They will hit the walls more often, which will create more collisions, more pressure. So we went from 1 atmosphere to 2 atmospheres because we lowered the pressure, increased the volume. Boyle's law. So the second law that we want to think about is something called Charles' law, and this is the relationship between volume and temperature. So we can use this to explain things like why does hot air rise, right? But let's look at the relationship first. So hot air rises because the volume of the gas sample at constant pressure, right? So if volume and temperature are what we're looking at, that means pressure and the amount of gas must be constant. So pressure and moles are constant. So as the volume of the gas sample at constant pressure increases with increasing temperature. So I raise the temperature, the volume goes up, and as long as the amount of gas stays the same, right, which is constant, the warming of the gas will cause a decrease in the density because of the volume going up, right? So if we imagine this, right, we imagine the volume increasing. So we go from, say, having a balloon like this with a certain number of gas molecules in it. As we raise the temperature, right, so we increase the temperature, the molecules will move faster, they will create more collisions, but the pressure has to stay constant. So the way that happens is, in order to keep the pressure constant, the volume goes up via Boyle's law, and so the net effect, right, is that as the temperature goes up, the volume goes up. Okay? Now, the density part of this, right, is you have the same number of molecules in more volume, so density equals mass over volume, and so mass is the same, volume is bigger. So if we take the same number and put it over a bigger number, right, the density will get smaller. And so we get a smaller density, right? And if the density of this gas gets low enough, gets lower than air, it will rise, just in the same way that something that is lower density than water will float, right? Something that is lower density in air will rise, and so this hot air that's lower in density will rise to the top, just like wood floats on the water. So this is how we explain sort of hot air rising in general. It's how we can explain the behavior or how hot air balloons work, right? Is we heat up the air, it expands the balloon, the air becomes less dense, and eventually it becomes less dense than the air, and it rises. Right? And it'll float, right? That warm air will rise in the cooler air and will float. So Charles, right, put this into measurements, right? He established this relationship that we could observe, and so forth. So it's called Charles' law. And again, he demonstrated that at constant pressure and a constant amount of gas, that the volume of a gas and its, this is important, Kelvin, as I mentioned earlier, Kelvin temperature are directly proportional. So we can illustrate it like this. The volume is directly proportional to the temperature. In other words, they move in the same direction. Right? Temperature goes up, volume goes up, temperature goes down, volume goes down. Now, both of these, Charles' law and Boyle's law, give us direct relationships, or what we might call linear relationships, meaning that whatever amount that we change one variable by, the other one changes in the same by the same amount. So if we think back to Boyle's law, we said that as the pressure went up, the volume would go down. So, for example, if I double the pressure, then the volume will be 1/2. So if I put numbers to that, right, if I take the pressure from 1 atmosphere to 2 atmospheres, right, the volume would be cut in half. Right? And so whatever factor I change one of them by, the other one is going to change by the same factor, but for Boyle's law, in the opposite direction. So in Charles' law, it's the same idea, but since it's a direct relationship, if I change the temperature by some amount, say I double the temperature, then the volume will move in that same direction by the same factor, and the volume will double. So when we work with these two laws, a lot of the times we can look at these relationships and not even have to do any math problems if they give us simple relationships. So if they tell me that I double the volume of a gas, well, I know my pressure is going to drop by 1/2, right? It's going to drop by the same, it's going to go in the opposite direction by the same amount. If I raise the volume 4 times, then the pressure is going to drop to 1/4. Right? Or in the same way with Charles' law, if I triple the temperature, the volume will also triple, right? So there's this nice linear relationships in these two laws. So if we look back at Charles' law a little bit more, we can look at a demonstration of this, right? We can look at something like gas in a balloon. And if I put the balloon on an ice bath, right, where it has a relatively small volume, right, the molecules are moving slow, right, and I put that on above hot water, all of a sudden these molecules move faster. They start colliding with the surface more, so one of the first effects we see here is more collisions, which equals more pressure. Now, if we think about Boyle's law for a second, right? If there's more pressure, but we need the pressure to stay constant, then the volume will go up to get the pressure to drop back down to where it was originally. So our net effect is that we have a bigger volume at this higher temperature in order to maintain a constant pressure. So when we're above, we're in relatively cooler, we're going to have a lower volume, right? Because we're having less collisions, and so to get that pressure, we need the volume to be smaller so that we can create more collisions at a lower temperature, and the exact opposite at higher temperatures. So I'm going to close off this section, at least in terms of explanation. We're going to do some practice problems here in a second, but in terms of explanation, I want to convert Boyle's law and Charles' law into actual mathematical equations, right? So if we look at Boyle's law, right? Remember it said that the pressure was inversely related to volume. And so if we have two different conditions, right? If we change the pressure of a system and we want to see how the volume responds, we're going to come up with the Boyle's law equation that looks like this, where the pressure at one situation times its volume equals the pressure at a second situation times its volume. So this is the Boyle's law equation. Now, for Charles' law, where we saw that volume and temperature were directly related, our equation is going to look like this. So as we change the volume or change the temperature, the volume will match it so that this ratio stays the same. So if temperature goes up by twice, then volume has to go up by twice to match it, right? So double this, we double that, so these two sides stay equal, right? So this is the Charles' law equation. Now, we can also combine these two equations into one equation, and this is called the combined gas law. And this is useful if we are changing two variables at once. So Boyle's law and Charles' law equations are useful if we're just looking at those two variables. But what if we are looking at all three? So what if we change two of these three? Well, then we need a new equation to relate that. And we just simply combine the two equations, so we get P V over T equals PV over T for two different situations. So we can account for the changes of two out of these three variables. So we get our combined gas law. So at this point, we're going to do a couple example problems. Okay, so for our first problem, we have something that looks like this. A cylinder applies a pressure of 3.5 atmosphere and has a volume of 5.0 liters. What is the volume if the pressure is increased to 7 atmospheres? So the first thing is to understand what we're looking at. I mean, what are we trying to chase here? So we're given a situation where we know the pressure and we know the volume. And then we're said we're going to change the pressure and we want to know what the new volume is, right? So what do we know that relates pressure and volume? Well, that's Boyle's law, right? So we can first identify this as a Boyle's law problem. And that tells us that we're going to want to use Boyle's law equation, right? P1 V1 equals P2 V2. Now, we need to identify what are the ones and what are the twos. Now, you can do this either way, but typically the way that I sort of standardize it is that the ones are the things that were given, right? The original ones, and the twos are what we're changing it into. So in that scenario, our P1 here would be our original pressure, 3.5 atms, and our P2, right, would be our 7 atms. Our V1 would be our 5 liters, right, that goes with the 3.5, and the V2, right, that's what we're trying to find out. So there's some different ways that we can relate this. So I'm going to rearrange the equation before I put numbers in, or you can put the numbers in and rearrange the equation. So let's do it like this. So I'm going to plug in my P1, 3.5 atm, times my V1, 5.0 liters, equals my P2, my 7.0 atm, times V2. So you could do your rearranging before you solve, or you could do it after. So I'm just going to do it before. And so I'm going to divide both sides here by 7 atmospheres. Okay. So to get it moved over here. So of course here it cancels, and what I'm left with is 3.5 atm times 5 liters over 7 atm equals V2. Now, if we think about our units here, our units of atmospheres will cancel. So when I do my math, 3.5 times 5 divided by 7, I get 2.5 liters equals V2. So if we think about whether that makes sense or not, right? So I increased the pressure. In fact, I doubled the pressure, right? So what I did was I doubled the pressure. I went from 3.5 to 7. So according to what we know, right, I would expect the volume to move in the opposite direction, right, for Boyle's law, and I would expect the volume to be cut to 1/2 of the original volume. And that's exactly what we see, right? It went from 5 to 2.5. And so yes, the result makes sense based on what we would expect. Okay, so here's another problem. So let's look at this problem. We have a balloon with a volume of 3.7 liters at an unknown temperature. If the temperature is changed to 0 degrees Celsius, the volume is 2.9 liters. What was the original temperature? So again, we have to know what kind of problem this is so that we know what equation that we want to use. So if we look at what we're given a volume of 3.7 at some temperature, and the temperature is changed to 0 and the volume goes to 2.11. So we're looking at a connection or the relationship between volume and temperature. So of course, that makes this a Charles law problem. So we're going to use our Charles law equation, right? Volume over temperature equals volume over temperature. And if we look at what we know, right? So our original volume, 3.7 liters. Our new volume, 2.9 liters. Our original temperature, right? That's the unknown here. And our final temperature, 0 degrees Celsius. Now, one of the tricky things here, or one of the things that I want to drive, is that remember when we're dealing with these gas laws and I'm dealing with temperature must be in Kelvin. So, if we take our temperature of 0 degrees Celsius and we convert it to Kelvin, remember, we're going to add 273.15. So we get a temperature of 273.15 Kelvin. So if we go now and plug some numbers in here, right, we get 3.7 liters over T1 equals 2.9 liters over 273.15 Kelvin. Now, again, we're going to do some math here, our little algebra. So we're going to try to we need to get T1 by itself. And it's easier if we do it on the top. So I'm going to show a couple steps here that might make it a little bit easier. So the first thing I'm going to do is I'm going to multiply both sides by T1. So let's do that. So I'm going to have T1 times 3.7 liters divided by T1 equals 2.9 liters times T1 over 273.15 Kelvin. And what we can see here is the T1 cancels over here. And what we're left with is 3.7 liters equals 2.9 liters times T1 over 273 Kelvin, or 273.15 Kelvin. So we continue to get T1 by itself. We're going to multiply both sides by 273.15. So we get 273.15 Kelvin times 3.7 liters equals 2.9 liters times T1 times 273.15 Kelvin divided by 273.15 Kelvin. We can then divide both sides by 2.9, right, to get rid of the 2.9. So we can divide this side by 2.9 liters, divide this side by 2.9 liters, and what we end up seeing here is that on this side the 2.9 cancels out, the 273.15 cancels out, and what we're left with is 273.15 Kelvin times 3.7 liters divided by 2.9 liters equals T1. So in terms of units, our liters cancel here, and we're left with T1 equals 348 Kelvin equals T1. So, if we want to think about whether this makes sense, if we think about what our original temperature was, right? 273, and we went to 348. Okay? Our volume, we lowered our volume, right? Our volume went down. So in order for the volume to go down, we would expect the temperature to go down as well. And so our temperature, again, this is our T1, started out at 348. It dropped down to 273. So it makes sense that our volume also dropped down from 3.7 to 2.9. All right, so let's do one final problem here. And it goes like this. A sample of a gas has an initial volume of 158 milliliters at a pressure of 735 millimeters of mercury and a temperature of 34 degrees Celsius. If the gas is compressed to 108 milliliters and the temperature is raised to 85 degrees Celsius, what is the final pressure in millimeters of mercury? All right, so again, as with all these problems, the first thing is we have to figure out what kind of problem we're dealing with. So in this case, we're given an initial sample and we're given a volume, we're given a pressure, and we're given a temperature. And we then change the volume and we change the temperature. And we want to figure out what the pressure does. So we're changing two things, right? We're changing temperature and we're changing volume. So we can't just use Boyle's law, right? That's just pressure and volume. We can't just use Charles' law because that's just volume and temperature. So this is where the combined law comes in. And so, right, so this would be a combined law problem. And so remember our combined law, right? P1 V1 over T1 equals P2 V2 over T2. So if we put our variables up here, right, and we know that our first volume, right, our V1, right, is 158 milliliters. And we know that our V2 is 108 milliliters. We know our T1, right, is 34 degrees Celsius. And we know our T2 is 85 degrees Celsius. And we know that our P1 is 735 millimeters of mercury. And our P2, right, is what we're trying to find. So, like we saw in the last problem, we have to convert we have to convert these temperatures in to Kelvin. So if we take 34 and we convert that into Kelvin, we're going to add the 273, and this becomes 307.15 Kelvin. And T2, again, we add, then becomes 358.15 Kelvin. And so now we can start plugging things in to our equation, right? So we plug in our P1, 735 millimeters of mercury. We have our V1, 158 milliliters. We have our T1, 307.15 Kelvin. And it equals our P2 times our V2 of 108 milliliters and 358.15 Kelvin. So we're going to solve our math here, right? We're going to isolate P2, so we're going to need to multiply both sides by the 358.15. We're going to divide both sides by the 108. And where we're going to end up here is our 358.15 Kelvin times 735 millimeters of mercury times 158 milliliters and then on the bottom we're going to have our 307.15 Kelvin divided by our 108 milliliters. And all on this side, that all equals P2. So in terms of the units, right, we see that Kelvin cancels out here, milliliters cancels out here, and so our units will be millimeters of mercury. So if we do all this, we do all the math, we put all this together, we come up with a final answer. Take a second and plug it into our calculator. We come up with a final answer of P2 equals 1,250 millimeters of mercury. Or you could rewrite this as 1.25 times 10 to the third millimeters of mercury. So there's an example of a combined gas law problem where we're changing two variables, in this case volume and temperature, and looking to see, in this case, how the pressure responds.